Hello viewers, welcome back to my channel Shraddha's Physics. Here we are continuing our lecture with the nuclear physics of the unit 1. Today we will see the angular momentum of the nucleus. So before going to the topic, let me tell you, in case of an atom, the central part is called the nucleus, where the protons as well as the neutrons are present. Okay, so these are combinedly known as the protons as well as the neutrons. They combinedly known as the nucleons. Okay, these are called the nucleons. It may be protons or it may be neutrons. Okay, and the central part of an atom is called, this is called the nucleus. This as a whole called the nucleus, and the electrons, they are revolving around the nucleus. So this is the basic structure of the nucleus. This is the basic structure of the atom. Now let us see what is the angular momentum of the nucleus. The nucleus consists of protons as well as the neutrons. So the neutron and proton, it possesses an intrinsic angular momentum due to the spinning motion of the nucleon about an axis passing through its center of mass, and that is called the spin angular momentum. So it may be neutron or it may be proton. Suppose this is your neutron, or it may be called as your proton. So in case of neutron, it has no charge or it is neutral in nature. But in case of proton, it has positive charge. Okay. Now suppose this is the axis of the proton, or you may say that it may be proton or it may be neutron. Okay. Suppose in this case, this is the axis passing through the proton, and it will spin about this axis. And because of this spinning motion, it will possesses the spin angular momentum. So now we can say that the spin angular momentum magnitude, it can be expressed as S will be equal to the magnitude of S, this is your capital S, that is the spin angular momentum. This is equal to small s into s plus 1 root over into h cot. This is your s into s plus 1 root over h cot. This is your small s, and this small s, it is called as the spin quantum number. Okay, this small s is called as the spin quantum number, and its only value is 1 by 2. Its only value, half is its only value, that is one value is its here 1 by 2. It has only one value. Now the component of s vector along the magnetic field parallel to the z direction. So the s component, we can write sz will be equal to the magnitude along the parallel direction to the magnetic field, that is the along the z direction. Sz will be equal to ms into h cot. Okay, this h cot is nothing but your h by 2 pi, and this sometimes is read as, this is your h bar. Okay, this is h bar, and this ms equal to the spin magnetic quantum number, and it has the and it has the values like 2s plus 1. That is, if you substitute the value s equal to 1 by 2, then this will be 2 into 1 by 2 plus 1. That will be 1 plus 1, that is equal to 2 values. So here we can say that this spin magnetic quantum number ms has two values. That is, one is your plus s and another is your minus s. This small s is your quantum number, spin quantum number. So ms has the two values, that will be plus 1 by 2 and another one is your minus 1 by 2. Simply, if I will substitute this value in equation 2, this is your equation 2, here you can see sz equal to ms h cot. So this sz will be equal to plus 1 by 2 h cot and sz will be equal to minus 1 by 2 h cot. So there will be the two values, that is the component of s along the magnetic field that is parallel to the z direction. It has two values, one will be plus half h cot, another will be minus half h cot. That is, one may be up spin or another may be down spin. So this is because of the spinning motion of the nucleon. I am saying nucleon, because of the spinning motion of the nucleon, spin angular momentum occurs. Similarly, in the nucleus, the orbital, suppose here consider, this is suppose the nucleus, and inside this nucleus, if you will consider any nucleon, that is, it may be proton or neutron, it may be in motion like this. Okay, it will move in this way. So because of its orbital motion, it will possesses orbital angular momentum. It will possesses orbital angular momentum because of its spin. That is, when it will rotate about this axis, then it will possess a spin angular momentum, and because of its orbital motion, when it will move in this orbit, then it will possess orbital angular momentum. So now we can say each individual nucleon has the angular momentum associated with its orbital motion within that nucleus, and that is called the orbital angular momentum. Okay. Now we can write the magnitude of this orbital angular momentum will be equal to, that is your capital L. Okay, for the angular momentum I am using capital L. This is your orbital angular momentum. Similarly for your spin angular momentum, here I am representing capital S. Okay. So now this L will be equal to L into L plus 1 root over into h. This small l represents the quantum number of orbital quantum number. Small l is your orbital quantum number. As in case of the spin angular momentum, small s represents the spin quantum number. Similarly, for small l, it will represent the orbital quantum number, and it has the values like 0, 1, 2, 3, 4 and so on. Only the integral values exist here, and it will start from the 0, so up to 0, 1, 2, so on, up to infinite. So only the integral values are exist for the L, that is the orbital quantum number. Similarly, the component of L vector along the magnetic field parallel to the z direction, we can write Lz will be equal to ml h cot. So we can write ml h cot. So ml is here represents the orbital magnetic quantum number. M is for magnetic. So ml represents the orbital magnetic quantum number, and it has 2l plus 1 values, and that is from l minus 1 to l plus 1 values including 0. That is the 2l plus 1 values means it is your 0 plus or minus 1 plus or minus 2 and so on. Okay. So this is your orbital magnetic quantum number. Now if you will add vectorially, that is if you will add the orbital angular momentum with the spin angular momentum, then you will get the total angular momentum, that is z. So the total angular momentum j vector of a nucleon is the vector sum of the orbital and the spin angular momenta. Okay, this momenta is the plural form of angular momentum. So this is your summation of these two. The magnitude we can write, the magnitude of the j, that is the total angular momentum, we can represent like this is your j into j plus 1 root over into h cot. This is your j into j plus 1 root over h cot. This capital J represents the total angular momentum, and this small j represents the total angular momentum quantum number. Now the component of j vector along the magnetic field parallel to the z direction is, we can write jz equal to mj h cot. Okay, this is your jz equal to mj h cot, where mj equal to the magnetic total angular momentum quantum number. This is your magnetic total angular momentum quantum number. M is for magnetic, j represents the total angular momentum, and this is your small mj. So small j means this is your quantum number. Small j represents total angular momentum quantum number. Okay, and it has 2j plus 1 values, that is it varies from j minus 1 to j plus 1 values including 0. Now if we will consider the total angular momentum of the nucleus, this is the nucleus, capital I vector for a particular nucleus state, it is the resultant of the individual total angular momentum of all the constituent nucleons in the nucleus. So what is the difference between j and I? So this j is nothing but the sum of L and S, that is vectorially if I will add, this j represents total angular momentum of the nucleon, and here this I represents the total angular momentum of the nucleus. So the magnitude of this I will be equal to I into I plus 1 root over into h cot. Here this small I is the total angular momentum quantum number of the nucleus. So as a whole, if I will consider the total nucleus, so for the nucleus, if I will consider the whole nucleus, then the total angular momentum of this nucleus, it is represented by I. But if you will consider first the orbital motion, then spin motion, then after that if you will add these two, then you will get the total angular momentum of the nucleons. Okay, this is the basic difference between these two. This I represents the total angular momentum of the nucleus, and also this is called the nuclear spin. This vector I vector represents the nuclear spin, and its value will be equal to, if it is even, that is when A value is even, then the nuclear spin will be equal to integral multiple of h cot, that is represented as nh cot, and when this A value is odd, then this nuclear spin will be equal to, this is your odd integral of h cot, or that is your 2n plus 1 into h cot by 2. So here it will have also the two values, that is nh cot or 2n plus 1 h cot by 2. When A value is even, A means your atomic mass. Okay, when A is even, then the spin will be equal to nh cot, and when this A equal to odd, then I equal to 2n plus 1 into h cot by 2, where n represents or n denotes the integer. Okay, so this is all for today. Thank you.